Hello students, welcome to physics class. Today we are deriving an equation for magnetic field produced by a current carrying circular coil by using Biot-Savart law. For that, here we have a current carrying circular coil of radius A, and this circular coil is placed in such a way that its plane is perpendicular to the plane of this board. The circular coil is placed in such a way that the plane of the coil is perpendicular to the plane of this board. A is the radius of the circular coil and I current is passing through the circular coil. Now we want to find what is the magnetic field, what is the intensity of magnetic field at a point P at a distance r from the center of the circular coil. The point P lies at a distance r from the center of the circular coil on the axis of the circular coil. So, to apply this Biot-Savart law, first we are taking a very small current carrying element, say dl is a very small current carrying element, and you know that the direction of that current carrying element is taken as the direction of the current. So, this is the direction of the current in the circular coil. This is the direction of current I, and so the direction of dl is in the same direction of I. Now you can see that dl and this position vector to this point, say the position vector to this point is S. The position vector to this point is marked as S, vector S, or the magnitude is S. Now you can see that dl and S are perpendicular to each other. dl and S are perpendicular to each other. The direction of dl is along the direction of I and S is perpendicular to dl. So first, if you are finding what is the magnetic field at the point P produced by this two small element dl, so apply Biot-Savart law. We know that by Biot-Savart law, the magnetic field at the point P due to dl is given by dB is equal to mu 0 by 4 pi I dl sin theta by distance square. The distance to this point P is S from the element dl. And we already told that the angle between dl and S is 90. dl and S are perpendicular to each other. So the theta is equal to 90. The value of theta is equal to 90. So sin theta become 1. So the magnetic field is dB is equal to mu 0 by 4 pi I dl by S square. The reason sin theta is equal to 1 since theta is equal to 90 degree. Now you see that dB is given by dB is equal to mu 0 by 4 pi I dl by S square. And dB is perpendicular to S. The dB is perpendicular to S and lies in this plane of this board. dB is perpendicular to this S and lies in this plane of this board, which is given as PQ. dB is given as PQ, which lies in this plane of this board and perpendicular to S. Now we are resolving dB into two components. One is its horizontal component and other is its vertical component. Now suppose if you are taking this angle is phi and this angle is also phi. Now once we are resolved this dB into dB sin phi, which is along this axis, and dB cos phi, which is perpendicular to this axis. This is the angle phi. Once we are resolving dB, this component is dB sin phi, which lies along this axis, and dB cos phi, which is perpendicular to this axis. Okay, that is the dB is resolved into dB sin phi along the axis and dB cos phi perpendicular to the axis. Now suppose if you are considering a diametrically opposite point dl for this element dl, choose another diametrically opposite element dl. This dl is also produce a magnetic field here. The dl also produce a magnetic field at this point P. Once you have resolved this magnetic field dB into horizontal and vertical component, its horizontal component, that is dB sin phi, which lies along this axis, and we have vertical component dB cos phi, which is perpendicular to this axis. Now you can see that the dB sin phi are in same direction. For both this element dl, the dB sin phi are in same direction, but dB cos phi are in opposite direction. So what happened? The dB cos phi getting cancelled because they are equal in magnitude and opposite in direction. Whereas dB sin phi are in same direction, so they're getting added. So if you are considering all such a diametrically opposite points on the circular coil, the dB sin phi is getting added and dB cos phi getting cancelled. So if you are finding what's the total magnetic field at this point P produced by all such as very small element dl, we have to consider only the sign component. All cos components are getting cancelled and add all sign components. So we can write the total magnetic field B is equal to integral dB sin phi. Integral dB sin phi. Substitute the value of dB. dB is equal to mu 0 by 4 pi I dl by s square, and substitute for sin phi. From this diagram, phi, sin phi is equal to A by S. Opposite side by adjacent side, that's A by S. So dB is equal to mu 0 by 4 pi I dl by s square, and sin phi is equal to A by S. And keep all other constant here, that's mu 0 by 4 pi I, A, and s raised to 3, s cube are constant. So we keeping out and writing integral dl. What's integral dl? Sum of the such a small element dl. So the total length of the circular coil. The total length of the circular coil is equal to 2 pi a. That's integral dl is equal to 2 pi a. That's b is equal to mu 0 by 4 pi I a by s square into I by I a by s raised to 3 actually s cube into 2 pi a. That become mu 0 I a square by 2s raised to 3. 2s raised to 3. Now substitute for s. The value of s can be written in terms of a and r. A is the radius and r is the distance to this point. So how can you write? S is equal to root of r square plus a square. That is, s is equal to r square plus a square whole raised to 1 by 2. It means root of r square plus a square. So instead of s, substitute that value, that is r square plus a square whole raised to 3 by 2. S cube become whole raised to 3 by 2. So that's the magnetic field at this point P. And so what the direction of that magnetic field? The direction of this magnetic field is along the axis. It lies in this plane and along the axis of the circular coil. The direction is along the axis. Since it is here on x-axis, so if you want, you can write as plus I is along positive x-axis. So if it have a n number of turns, instead of taking a single turn, if the coil having n number of turns, we can write B is equal to mu 0 n I a square divided by 2 into r square plus a square whole raised to 3 by 2, because all the circular coil produce a magnetic field in the same direction as produced by a single coil. So as they are vector directed along the same direction, so add all vectors. So the total magnetic field is equal to n times of magnetic field produced by a single coil. So this is the total magnetic field produced by n coil, that is mu 0 n I a square divided by 2 into r square plus a square whole raised to 3 by 2. What is mu 0? Mu 0 is the permeability of free space, n the number of turns, I the current passing through this coil, a the radius of this coil, and r is the distance to that point. Now discuss some special cases. Okay, suppose the r is equal to 0. R is equal to 0. What is r? R is the distance to that point. If that point lies at the center itself, that means the point lies at the center itself, then substitute in this equation r is equal to 0. Substitute r is equal to 0. Now it become mu 0 n I a square whole raised to 3 by 2 is the, so it become a raised to 3. So a square and a raised to 3 is getting cancelled. So we're getting B is equal to mu 0 n I divided by A. Mu 0 n I divided by A. That is, the magnetic field at the center of this circular coil is given by mu 0 n I divided by A. And another special case, if the distance to this point is too large, that is R is very much greater than A. So we can neglect this A. We can neglect this A. So mu 0 n I A square into 2 times of R square whole raised to 3 by 2. R square whole raised to 3 by 2 become R raised to 3. So if the point lies far away from the center, this is the expression for the magnetic field. B is equal to mu 0 n I A square divided by 2 R raised to 3. One more case. Suppose we are taking this, the radius is equal to R is equal to A. The condition R is equal to A. R is equal to A. So mu 0 n I A square. So instead of this R, we are writing A itself. So 2 times of A square plus A square whole raised to 3 by 2. So this one can also rewrite like this way. Mu 0 n I divided by 2 raised to 5 by 2 into A. 2 raised to 5 by 2 into A. That are the some special cases. That is, magnetic field produced by a circular coil is directed along the axis of the circular coil. Now see the direction of magnetic field produced by a current carrying circular coil. We already derived the expression for the magnetic field produced by a circular coil, and you know that it lies along the axis of the circular coil. And so the direction of magnetic field is shown by using a magnetic lines of force. Here we have a circular coil here which is placed in such a way that the plane of the coil is parallel to the plane of this paper or plane of this board. So this is the direction of current. This is the direction of current. So the magnetic field lines are shown here. You can see that near to the conductor or near to the current carrying conductor, the magnetic field lines are concentric circle. That is, near to the conductor, the magnetic field lines are shown as concentric circle. As we move towards the center, radially, if you move towards the center of the circular coil, you can see the concentric circle or radius of the circle become larger and larger or become less curved. Exact at the center, I just shown this as a straight line. That is, the curvature this decreases and become almost curveless, or it become almost a straight line when the point is at the center. So this is the pattern of magnetic field lines due to a circular coil or current carrying circular coil. And we can predict the direction of magnetic field produced by a circular coil by a right hand thumb rule. By right hand thumb rule. Let us see how to apply the right hand thumb rule here. To apply this right hand thumb rule, we have to stretch our right hand, or we have to hold our right hand in such a way that stretch all the fingers on the right hand in the direction of current. Then the thumb point in the direction of magnetic field. Here the coil is placed, suppose this is a plane of your paper and the circular coil is placed here. If you hold all the curved fingers like this in such a way that the curved finger indicate the direction of current and the thumb indicate the direction of magnetic field. So in that way, we can find the direction of magnetic field. If the current is flowing like this way, in this direction, hold your curved fingers in such a way that the thumb direct the direction of magnetic field. So that direction of magnetic field is like this. So that is the right hand thumb rule for finding the magnetic field direction due to a circular coil. And in this diagram, the variation of magnetic field from the center of the circular coil with a distance is given here. The distance is taken from the center of the circular coil and the magnetic field is taken on this axis. And you can see that magnetic field is maximum at the center. The magnetic field is maximum at the center of the circular coil, and in both direction, when we are moving away from the center, the magnitude of magnetic field is decreases. So this is the variation of magnetic field as we moving away from the center of the circular coil. The magnetic field is maximum at the center, and in both direction we have magnetic field. On both sides we have magnetic field, and the magnitude is decreases when you are moving away from the center of the circular coil. That's the nature of the magnetic field produced by a circular coil. That's all today. Thank you.